Okay, welcome to this video in which we will show how to apply ad hoc analysis to find a voltage and a current in a circuit with two independent sources. If you have two independent sources in a circuit and you don't have a single loop or a single node circuit, using ad hoc analysis can get sort of complicated, as we will demonstrate. It turns out that what we'll have to do is write down voltages and currents and so on in terms of an unknown and then solve for that unknown. Sometimes you'll find it's actually just easier to go ahead and apply nodal analysis. Of course, if your instructor is requiring to use this or solve such a circuit without using nodal analysis, or you don't know nodal analysis, this is probably your best bet. So if you look at this circuit, what I want to do is I want to find the current I and the voltage V, the current I that goes through this 5K ohm resistor, and then the voltage V across this 5K ohm resistor. And there's many things that I could choose as my unknown. For this, we'll choose I to be our unknown. Okay. Now, there's still a lot of different things we could try, and having actually worked this once and come to an answer that I thought was wrong but actually turned out to be right, I will do the following. The first thing that I will do is apply Kirchhoff's current law to this node right here. And in order to do that, I will define a current that goes through this 10K ohm resistor, and I'll call it, say, I1. Now, if I look at this, I have I1 going into the node, and that is equal to I, which is the current leaving the node, plus 2 milliamps. And why can I say 2 milliamps? Well, the current through this current source is 2 milliamps. This current source will have whatever voltage is necessary to make the rest of the circuit always make sure that there's 2 milliamps flowing through it. And this current source is in series with this 3K ohm resistor. So any current that flows through the source has to flow through the resistor, okay, because there's no place else for the current to go. And if that's the case, that means that the current leaving the green node along this path is 2 milliamps, because that's what the current source constrains it to be. So that's how I get the idea that the current through the 10K ohm resistor is equal to I plus 2 milliamps. Again, I applied KCL here to get this, Kirchhoff's current law. Okay. Once I know what this current is, I can find out what the voltage across the 10K ohm resistor is using Ohm's law. So the voltage, let me call this V1. The voltage across this 10K ohm resistor is going to be the current through the resistor times 10K ohm. And I know that this is going to be 10K ohms, and I can plug this expression in for I1. So this is going to be 10K ohms times I plus 2 milliamps. Okay, so that tells me that the voltage across this 10K ohm resistor is given by something that depends on I. Why do I want to know that? Well, I also know that the voltage across the 5K ohm resistor is I times 5K ohms. And what I can do now is apply Kirchhoff's voltage law around this loop that includes the 10K ohm resistor, this 5K ohm resistor, and our 3-volt source. And if I do that, I have V1, that's the voltage across the 10K ohm resistor. I'm going from positive to negative, plus V, which is the voltage across the 5K ohm resistor, minus 3 volts. I have a negative sign here because I'm going from negative to plus on the 3 volt source, is equal to 0. Okay. Now I know what V is in terms of I. It's given by this. I know what V1 is in terms of I. It's given by this. I actually can now substitute everything that I know into this equation and have one equation in terms of I. Since I have one equation with one unknown, I can solve it for I and we'll be done. Well, we still have to find V, but that's not very hard. So let's see. V1 is going to be this 10K ohms times I plus 2 milliamps. Now we have to add V, which is I times 5K ohms. And we'll say that this is equal to 3 volts. Okay. So that's our equation. It involves one unknown, which is I, and we can solve it then. So let's see. Where should we solve it? Well, I don't want to erase a bunch of stuff yet. Oh, no, I can actually erase almost everything. Okay. So let's get rid of this stuff to make room. And let's take this equation that we just got and work it out and solve for I. So I can write this as 10K ohms times I plus 10K ohms times 2 milliamps. Okay, this is going to be 10 times 10 to the third ohms times 2 times 10 to the minus third amps, which will end up being 20 volts. Okay. So this then is going to be 20 volts plus I times 5K ohms, and this is equal to 3 volts. Okay. I can combine the terms that depend on I. They both have a factor of I. So I'll have I times 10K ohms plus 5K ohms is equal to this 3 volts minus 20 volts. And doing the algebra, I end up with I is equal to minus 17 volts over 15K ohms, which when I work that out with my trusty Google calculator, I get that this is 0.00133 amps. But being an electrical engineer, I actually like to write this better as 1.33 milliamps. Okay, so basically we've been able to solve for I. Isn't that exciting? So the only thing left to do then is to go back to this equation and solve for V. Okay, we know that V will be equal to I, which is 1.33 milliamps. Oops, this is bad. Very, very bad. I lost a negative sign there, and so I lost a negative sign there. So I lost a negative sign there. Times 5K ohms. Okay, so I work this out. And I get that V is negative 5.67 volts. Okay, so I've actually found what I set out to find. I found I, which is, here, let's find a nice color for highlighting stuff. Oh, gosh, I just don't know. It's nice blue. So I found I, and I found V. Now, I and V are both negative. Is that a bad thing? Does that mean that I've made a mistake? Have I screwed up somewhere? And the answer is it could, but it's not an issue here. I've actually checked my work before I started recording this, and this is correct. All it means is that if the voltage is negative, I've drawn it with plus on top and minus on bottom, but what that really means is that this point of the resistor has a higher potential than this point. This point is higher by 5.67 volts than this point. I've also found that my current is negative. Is that a problem? No. It just means that the direction I've drawn the arrow is not the direction the current actually flows. The current is actually flowing this direction through the resistor with 1.33 milliamps. So this is the beauty of being able to do circuit analysis mathematically. If you draw pictures where you label the voltage and currents incorrectly, in the sense that you put a plus and a minus where in such a way that the actual potential drop across the resistor is the opposite of that, or you draw a current so that the current's actually flowing in the opposite direction, the circuit analysis will tell you by just giving you a negative value for your result. So this concludes the ad hoc analysis of two independent sources video. Hopefully you found it useful.